Okay, now we cover the last section of this chapter. It's about the convolution of two functions. So the definition of convolutions is given as follows. Suppose we have two functions, f and g, and they are measurable functions defined over the Rn. We can also define this f and g over a subset of Rn, but in that case, we can just consider this f as for example, if f is actually defined over E, then we consider this f as defined over Rn, but we multiply this f by the characteristic function of E. So you can still consider this as a function over R, defined over Rn. Okay, so in general, we consider these two functions defined over the Rn, and we call this following integral a convolution of f and g. So for every fixed x, the integral here is a function of x, right? For every fixed x, we'll take the integral here, we'll get a scalar. And if we define such a function that for every x, the value of that function at the point x is equal to this, then this function we define is called a convolution of f and g. And this function is denoted by this f star and g. Okay? And this apparently requires that the integral exists for every x. It could be positive infinity and negative infinity as well, but it must exist. That means this one must be integrable. All right. One thing that we know is that the convolution of two functions it does not depend on the order. So the convolution of f and g is equal to the convolution of g and f. Okay? The reason is, say we have the convolution of f and g. So remember that this is the function of x. It's again a function defined. So f star g is again a function from Rn to R. Okay, it's just for each fixed x, you take the integral as we define. That's how we define this function, right? Then we can check the integral, the convolution of f and g according to our definition is equal to the integral of Rn. This is f of x minus y gy dy, right? We can always think this as we have y equals to y1 through yn. It has n components. So right, then this just means that the integral negative to infinity to positive infinity for each of these y components would have x minus y gy dy1 through dyn. Okay, so you can always interpret in this way. All right, so we can do, in this case, we can do a change of variable. For example, we can set x minus y equals to z, and in this case, this will become the integral of f x minus y becomes z. So this is just f of z, and g is y. So the x minus y equals to z. That means y equals to x minus z, right? So this is equivalent to y equals to x minus z. So I can replace the y with the x minus z, and then dy becomes dx minus d, becomes minus dz because x is fixed. So we have the negative dz right here, right? But remember that the limit here, this indicates the limit. For example, this limit indicates the limit of yn. The yn is from negative infinity to positive infinity, but since x, y and z are related in this way, so that means the zn will range from to here. This y, say for each component, xi minus yi equals to zi for each I. So when the y goes from negative infinity to positive infinity, the zi goes from positive infinity to negative infinity, right? So we'll flip the limit right here. So we'll flip all those limits as well. So the integral here is actually the d negative times dz1 through dzn, and here we'll have the positive infinity to negative infinity for each one of them. And then the negative can be pulled out, and for each one of them will just become this. Okay, just go back to the normal. And we have f of z, g of x minus z dz. And then z is just a symbol, so it's essentially just equal to the convolution of g and f and x. Okay, that's why the convolution actually is commutable. So it's pretty much like a product of the two, but it's actually defined in the integral of the product of two functions in this way. But you can exchange the order of these two functions. Okay, so that's something you probably have seen before, either in calculus or in analysis. But here we're going to study the behavior of this convolution. Actually, we only give two results. The first result is if the two functions f and g are integrable, then the convolution of these two functions is finite everywhere, and we can actually estimate the integral of this function. So this is given by the following theorem. If f and g are integrable functions, then the convolution of these two is finite almost everywhere on this Rn. And also the integral of the convolution is less than equal to, apparently this is in Rn, is less than equal to the product of their own integrals. Okay, so let's see how to prove this. So that means if the two functions are integrable, then the integral, the convolution is also integrable, and you actually have a bound for the convolution, which is just this right-hand side, just the product of their own integrals. Okay, so we take the absolute value here, but let's say that suppose f and g are both non-negative functions, then apparently we can temporarily forget the absolute values and just focus on this inequality. So we first consider the case where f and g are both non-negative functions. Then we can check the convolution of f and g at the x dx. So according to our definition, the convolution of the two itself is defined as a convolution, but the x is fixed and the variable is y. So the integrand here in the parentheses, the whole thing in the parentheses is a convolution of f and g dx. Okay, and because of the tonality theorem we discussed before, as long as the functions, the integrand is a negative function, then we can freely exchange the order of integration. So we can take the integration with respect to x first instead of y first. So this is equal to the integral of. You can see that only the f involves the point x. So we can take the integral for f first, and then the dy. And apparently here, this part gives us, for every fixed y, this part just gives us the integral of f over the entire domain, entire space Rn. So this whole thing here will be independent of y. Okay, so that's why we can actually move it out. It's a constant. We can move it out. So it's just the integral of this f of x minus y dx, but it's actually essentially just the f of x, since we can just shift the point x minus y to x. Okay, so that's just this. Right, so that's the integral I just described. This is just an integral here, and then we also have an integral for the other term, which is gy dy, this term. Okay, so the constant is pulled out, and what's ever left is this. So it's just a product of the two integrals, as we wanted, right? And since the two functions are integrable, so both of these two terms are finite, so the product of them is still finite. So in this case, it's easy to show that the estimate we have in the theorem is true for non-negative functions. But for general functions, f and g, we can see that the integral of this absolute value of the convolution, so essentially just this dx, and this is equal to the integral of this convolution as in the definition, and apparently this is bounded about by, so this is Rn, bounded about by this. We take the absolute value into the integrand. dy dx. Okay, and because f and g are both integrable, so their absolute values are also integrable. And that just means that these two are non-negative integrable functions. And we can use the result we just proved to show that this is actually bounded by the integral of the absolute value of f times the integral of the absolute value of g over Rn. Okay, and this completes the proof for general case where this f and g are not necessarily non-negative. Okay. Now give the next result. The convolution has a very powerful property. Is that when you take the convolution of the two functions, even neither of them is continuous. You take the convolution of them, it becomes continuous, and even more than that, it becomes uniformly continuous. So this is the common way to make a function smoother. Okay, it's commonly used in PD, partial differential equations, when the function is not smooth, not differentiable, or even not continuous. We take a convolution with some function, then it becomes continuous and differentiable. Okay, so the theorem says, this result says that suppose we have a function f that is integrable and g is measurable and bounded. I want to be more specific. It means it's uniformly bounded almost everywhere, which means that this means that there exists some f such that f is bounded by m almost everywhere. Okay, so this is what I mean by here, by uniformly bounded almost everywhere. Sometimes you see some author says it's just bounded almost everywhere. Usually that also means this, but this could be confused with the finite almost everywhere, because for each point, it is still a finite number. That means it's somehow bounded. It's not infinity. in that case, you may see some kind of confusion between the bounded everywhere and the finite everywhere. So to be more specific, if it's bounded by a fixed number over the entire space, almost everywhere, then we say it's uniformly bounded almost everywhere. Okay. Then the convolution, if we have a integrable function f and a measurable and a uniformly bounded function g, then the convolution of these two gives us a uniformly continuous function. Okay, so to prove this, you think of what do we need to get the uniform continuity. We want to show that if a function is uniformly continuous, we want to show that for any point x, and for any h that is sufficiently small, we want to show that this is less than epsilon. Okay, less than epsilon. For all the x in Rn and all the h sufficiently small usually means that h is between 0 and delta for some delta. Okay, so the full tense sentence is that for any epsilon, there exists some delta, positive delta, such that for any point x and any h less than delta, this one holds. Right, that's the uniform continuity. So we want to reach that. And now let's see what we can get. According to the definition, the integral here, the difference, absolute value of the difference is just the absolute value of the, according to the definition of convolution, is just this. It's just the f x plus h minus y gy dy, and the second term is just the original convolution, which is this. Right? And we want to see, eventually we want to see if this is true. This part is true. But now we see that this is just equal to the difference here, and apparently there is a common term gy. So, and this is less than or equal to the absolute value, integral of the absolute value of x minus plus h minus y minus f of x minus y times gy, because this is a common term. Right? And because this g is a bounded function, so we know that this thing here is uniformly bounded by m, it's independent of y. So that we only need to show that this part, so this is less than or equal to m times the integral of the absolute value of the difference here. And then we see something similar, familiar, right? Because this, it doesn't depend on x, because the y is ranging through from the old points in Rn. So the x doesn't really matter. What is really matters is only the h. But when h is small, we know that this the integration of the integral has this continuity. When you shift the function, so you have a function like this. We shift the function a little bit. This is something we proved before. You shift it by h, then you take the integral of the difference of these two functions. It will approach to 0 as h goes to 0. Right? This is what we proved before. And now you can see that I can just make this h small enough so that this whole thing here is less than epsilon over m. Then the product of these two will be just less than epsilon. Okay, and this is essentially the idea. To complete the proof, you just need to add up the things I just mentioned. Because the g is uniformly bounded by m, and f is continuous, then we know that for any epsilon, there exists some delta such that when h is smaller than delta, whenever h is smaller than delta, this term is smaller than epsilon over m, and then the product of these two will be less than epsilon. And that shows that this is less than epsilon whenever h is less than delta. And it doesn't depend on x. So this holds for any x. And this means that the capital F is uniformly continuous over the Rn. Okay, so that is the proof of this result. Okay, now we start a new chapter about sign measure and differentiations. The first concept is the sign measure and the decomposition of the sign measure. So first, we'll give a definition. A sign measure is kind of extension of the standard measure or the big measure we learned before. Or in other words, we can basically think of the sign measure as the difference of two measures, two Lebesgue measures. Okay, but we're going to give a formal definition. Suppose we have this xm is a measurable space. Okay, and this m is just a set of measurable functions, and m is a sigma algebra of the sign of those measurable sets. A function nu is a mapping from this m to R extended. The set of extended real numbers is called a signed measure. If the following three conditions hold. First, the empty set has a measure 0. Second, the sign measure mu can take only one of positive infinity and negative infinity. So you can map this any measurable set to a real number, positive or negative, and it could be even infinity. But if it takes infinity, positive infinity, for some set, then can never take negative infinity for any other sets. Okay, and similarly, if it takes the negative infinity for some set, then it can never take a positive infinity anymore. And the third is the countable additivity, just like the measures. For any countable family, of mutually disjoint set, EK. So that means that we have countably many sets here, E1 through infinity, and they are mutually disjoint. I should say for any, there is the mu of the union of these EKs is equal to the sum of the nu of EK. So each one of them could be positive or negative, but they take the sign measure of the union is equal to the sum of the sign measures if those sets are disjoint. Okay, so this is the same as the measure. The only difference is that right now the measure could take a negative value. Okay, and the second term here, as I said, you can basically think that this nu can be thought of as the mu1 minus mu2, where mu1, mu2 are two measures. And if you have both of them as positive infinity, then the difference of them will not make sense. So we will require one of them to be a finite measure. So it takes only finite values. So in this case, we could have either positive infinity minus some finite number, which is still positive infinity, or is some finite. If this one is finite, then this one could be positive infinity. Then the difference of this could be negative infinity, but never be positive infinity anymore. Okay, so that's the reason why we require the second item. All right, so this is, as I said, this is extension of the measure we learned before. And apparently, if this mu only takes the negative value, then this mu is just the regular measure. It's also called a positive measure, but it's actually the measure we learned before. Okay, By the way, we said that there could be different ways to define measures because we always have the liberty to scale a measure. For example, since we define a Lebesgue measure, we can define some scaling of this measure. For example, multiply 10 this measure by 10 will be still a measure. It satisfies all the conditions we have. You just change our way to measure the mass of a set or the size of a set, but it still satisfies all the conditions for the measure, right? So that's why we could have different measures defined on the different positive measures defined on the same set, the same measurable space, and then we can also take the difference of them. That can give us the signed measure here. Okay, so now let's since we give the definition here, we want to study the properties of it. The first property is similar to the regular measure or the positive measure. It's about the continuity. Okay, so what it says is that if ek is increasing, and the E is the limit of the ek, which is the union of the ek. Okay, we know this is just the limit of those eks, since it's monotone. Then the limit of the signed measure also convert to the signed measure of the limit. Okay, so that's the first item. Second item is if ek is decreasing and the E is just the intersection of those sets. Again, you know, in this case, it's just the same as the limit of ek, since it's monotone decreasing. And I also require the first one, or actually any one in every term in the sequence, to have a finite value. Then we can also show that the limit of the signed measure is equal to the measure of the signed measure of the limit. So these two are exactly the same as the measure we learned before, but since we're considered signed measure, so this mu could take negative value, but these two results still hold. Okay, let's see how to prove this. So let's first consider the case that where the set is increasing. Then we can denote the difference, which is the new parts that is made for every new ek. It's the ek minus all the previous EIs. Okay, we can take this. Then by countable additivity, which is a third property of the signed measure, we know the signed measure of E is just the signed measure of this union of ek, right? Because of this. And due to the way we define this dk, we actually can rewrite this union as a disjoint union of the dk's. Okay, and this, due to the countable additivity of the signed measure, has become the sum of the signed measure of dk. And this apparently is equal to the limit for the partial sum. But this partial sum here is just the nu of the union of the dj for j from 1 to k, and this, by definition of dj, is just the signed measure of E. So it's just the limit of the signed measure of ek. Okay, because each one of this is equal to the ek, so it's a signed measure of ek. Okay, and this is pretty. We should be very familiar with this. As long as we have the countable additivity, we can get this equality very easily. And similarly, if this ek is decreasing, then we can just rewrite the. So if ek is decreasing, then we can just define or denote the fk to be E1 minus ek, and then we can apply this first result to the fk, which is increasing now. And then, since the E1 has a finite measure, then it can be moved out of the limit and cancel out on the two sides, and then we can get the same result for the second item. Okay, so that's pretty much similar to what we did for measures. Okay, now we give an important definition for the signed measures, because the signed measures could take positive or negative values. So we want to check over the set X where the signed measure will always take positive value, where it could always take a negative value, and where the value of this doesn't matter is always a zero. So this is called the new positive or new negative or new null sets. Okay, so what this means is, suppose we have a signed measure defined over the measurable space. Suppose new is a signed measure on this measurable space. Then we say this E is called new positive if for any subset of E, the measure of this set is non-negative. Okay, so this is called mu positive set. Mu positive set. The E is called mu positive set. And similarly, if for any subset of E, the measure of the subset is less than or equal to 0, then we call this set E new negative. And if for any subset of E, the measure is equal to 0, then we call this set E mu null. Okay, so what is the meaning of this? Let's say that we have this as our x, okay, and we have something like this, where over here, over the left part, the mu takes a positive value. So over the point, it takes some measure. Okay, it's kind of functions defined over here, and take a negative value on the other part. Okay. And we say this set E is mu positive, means that the set E can only be something like over this part, over this set, because over this part the nu is always non-negative. So you take a subset of that, it's still non-negative. The measure is still negative, and this is in contrast to the case where you have a E like this, and then although even if the measure of E itself is positive, because the positive part cancel out the negative part, still have something left over. The measure of E is positive, but we can find some subset of E, such like this part. Then the measure over this part is less than 0. In this case, this set E is not mu positive. It's not mu positive. Okay, so that's roughly what the meaning of this is. Okay, so that's what we defined for new positive. And similarly, we can define, as I said, we can define new negative or new null sets. Okay, so we can do the same thing for negative. So new negative or new null. And in this case, we'll have the new f less than equal to 0 or new f equal to 0, respectively. Okay, now consider the lemma. This the lemma says that if a sequence of sets are positive or new positive, to be more specific, then the limit or the union of them is still new positive. Okay, so similarly, you can do the negative part, new negative. If the older sets are new negative, then the union of them is also new negative. How to prove this? According to our definition, we want to show this set is new negative, new positive. We just need to show that for every subset of this set, this union here, the measure is non-negative. Okay? We can say that for any let's first define this. Again, the increment of the sets, which is defined as the pk minus all the previous p. Okay, we denote this qk to be this. Then apparently the qk is a subset of pk, and because of its property, we know that since pk is new positive, the measure of qk is also positive. Right? That's what we know. But let's keep this for a moment. Then for any, we want to show that for any subset of this union, the measure of E is non-negative. Okay, and to show that, so just let's check. The measure of E, according to the fact that the E is a subset of pk, so this is just the intersection of E and this union, right? And because of the definition of qk, we can rewrite this union as a disjoint union of qk's. Okay, by the way, the q1 is just the p1 itself. Okay, and starting from q2, the qk only measures the increment part, which hasn't appeared in the previous case. This is the intersection. We know that we can pull out this union and take the intersection of E with each of these sets. Okay, remember that now these qk's are disjoint. So the intersection of E and qk is also disjointed with other intersections. So that's why we can pull out the union, becomes the summation of the sign measure of E and qk. Okay, and this is because the countable additivity of this sign measure new. And now you can see that intersection of E and qk is a subset of qk, which is a subset of pk. So this subset of qk is also a subset of pk. And it's a subset of pk means that this part is greater than or equal to 0. And that means this is greater than or equal to 0. For each of these terms, it's greater than or equal to 0, so the sum is also greater than or equal to 0. And that shows that for any subset E of this union, the sign measure is greater than or equal to 0. And that means the set here is mu positive. Okay, so this prepares us with important fact. Once we have positive sets, new positive sets, and taking the union, will still have a new positive set. And this will be used in the following theorem called the Han Decomposition Theorem. That's a very important result for signed matter. So what this theorem says is that for any signed matter over the measurable space X, we can always partition this X into two sets, two disjoint sets. And on one set, this signed measure is mu positive, and on the other side, this signed measure is negative. Okay? And this decomposition is kind of unique up to the symmetric difference equal to 0. So let me explain that in details, what that means. Suppose we have a signed measure X. So signed measure on the measurable space, then there exists a new positive set P means positive, and a new negative set N, such that the X is equal to the union of the two, and these two sets themselves do not overlap, so it's disjoint union of the two. And also, if we have another choice for this decomposition, so suppose P prime and N prime is another such pair, then we said that this kind of unique partition means that the symmetric difference of P and P prime is actually null. It's new null. Okay. And for simplicity, later we'll call this pair of decomposition the Han decomposition of the signed measure nu. Okay, so again, what this means, say again, this is set X, and the nu takes the positive, say on this part, and the negative on this part. But there's some middle range. For example, I partition this into this way. On the middle, the nu is just null over in the middle set. So in this case, you can call this whole part P and the rest the N, or you can call this part P and this part N. So the difference between the P in the first case and the P in the second case, or some other choices of P which interpolates these two, you can see that these two, the difference of these two is just this area, but this area is completely new now. Okay, and that means the nu will not give any measure over any set over there. So, so it doesn't matter where you want to plot this boundary, since those common area will not have any measure. The measure is always 0. Okay, so that's intuitive what the meaning here. Yes, but let's see how to prove this. So the proof is given with several steps. The first step is that let's assume the signed measure can only take negative infinity, cannot take a positive infinity. Otherwise, we can just consider the negative nu. Okay, so without loss of generality, we assume this nu can only take R or negative infinity. Okay, and then in this case, consider the set of new positive sets. Okay, and then we denote this by, we use another, this set is the set of all the measurable new positive sets. So the P is new positive. Means that for every subset of P, the standard measure nu on that set is non-negative. Okay, then we define say M to be the supremum of the measure, where P is in this family. Okay, then because this is supremum, we know that then there exists a sequence pk, which is from this family, such that the limit of this pk goes to this end, right? Because this is a limit, it's a supremum. That means that we can find a sequence of sets such that their sign measure are non-negative and they go to the end. Okay, and now because this is a this pk is a positive set, and I'm actually taking the union of any two positive sets is still a positive set, and that is very easy to show. Actually, we showed if we take the union of countably many of these sets, it's still a positive set. Okay, so we can define, for example, we can define the qk to be the union of I is from 1 to k, and then we know that qk will be nu positive, and then the union of the pk's will be also the union of qk's, which is also mu positive. But right now the qk is increasing, so the measure of this qk also converges to the measure of this union of these qk's. Okay, and that is the and in this case we can see that the measure will be non-decreasing, and they can go up as much as mu, because as much as m. The reason is this. For example, this goes to q, and the q is the union of this qk's, and then we know that this q is nu positive, so it belongs to the family P, and the measure of q must be less than equal to m. The reason is m is a supremum value. Okay, and but because this is equal to, on the other hand, this sign measure goes to this, and this is actually just the limit of the union of pk's, and they go to m. That's why this measure must go to m as well. So that's why this actually is equality. Okay, so you can reach to the equality when you take the partial union of them. But the point right now here is that if we take the union of this pk, we know that the pk will have a measure equal to m. Okay. Take this p to be the union of the pk. We know this p is still mu positive, and the measure of P will be equal to M. Okay, you can prove this by what I just said here. It's just not difficult. Okay, now with this, we can proceed to the next step. Next step says that we want to claim, that N to be the complement of P. They want to claim that we already showed that P is nu positive. We just need to show that N is nu negative. Okay, we need to show that the set N is nu negative. Okay, so to show this set is nu negative, we need to show that for any subset of N, the measure over that subset is negative. Okay, so if this is not true, if E is a subset of N and the measure of E is positive, then we can claim that the E cannot be nu positive. So what this means is, again, suppose we have the picture as before, and we have this part as the P, which is the union of the pKs, and then on this part we will have the N. If we can have some subset here, it's the E, and this E is nu positive, then we can put this E together with that P. Okay, we can put the P and the E together, then the union of P and the E is also nu positive. Because P and E are both mu positive, so the union of them is pure positive. And because these two sides are disjoint, since the E is in the complement of P, we know the intersection of these two is empty. So the sign measure of the two is equal to the sign measure of P plus the sign measure of E, right? This the nu is countable additive, and we have two disjoint sets now. So the measure of the union is equal to the sum of their measures. And apparently because nu E is greater than 0, this means that's greater than P itself, which is equal to M. And now we found a nu positive set here, which has a measure bigger than M, but this M is supposed to be the supremum of all the sign measure of mu positive sets, so this is not possible, right? So that's where the contradiction is. So that means even if you can find some subset of N such that the measure of the subset is positive, this E here cannot be mu positive. Okay, this E cannot be a mu positive set. But it's still possible that you have find a subset of E and the measure of E is positive. It's just that this E is not a mu positive set. And we can still get some contradiction from there. But at least what we show so far is that if the set E has a positive measure, it cannot be nu positive. Okay. Okay, because we said this E is not mu positive, even if it itself has a positive measure, that means there exists some subset of E, we call it B, and this B has a negative measure. So there exists a subset B of E such that the measure of B is negative. And the reason is, if all the subset of E has a non-negative measure, then this E is new positive, and that's what we just showed. That's not possible, right? So that's why there must be some subset B, which has a negative measure. And in this case, we can just take out this B and use whatever we left inside the E, and that part will have an even bigger measure. The reason is, if we let the leftover to be A, then we know that the measure of A, according to countable additivity, we know this is just the mu of E minus nu of B. But we know that the nu of B is negative, so the minus nu of B will be positive, so it will be bigger than nu of E. Okay, so what we said so far is that if a subset of N has a positive measure like this, then we can take out some part of E and make this measure even larger. Okay, even more positive. So this is the property we just showed. And there we're going to use this property to get a contradiction for the original statement. We want to get a contradiction if this nu is not nu, if N is not nu negative. Okay. Okay. So if N is not nu negative, then we know that there exists some subset of N such that the measure of this A0 is bigger than 0. Right? Otherwise, it will be just nu negative. If any subset has a negative, non-positive measure, then this set N is nu negative. But if it's not, then must be some set A0, such that its measure is greater than 0. Okay, so A0 is a subset of N. What we just showed before is that if the subset is a subset of N and it has a positive net measure, that means we can take out some part and make this measure even bigger. Okay, let's say that the biggest case we can make is we choose this N1 to smallest possible smallest integer N1 such that there exists a subset of A0 and the measure of A1 is bigger than the measure of A0 plus 1 over A1, or 1 over N1. It's bigger than or equal to that. So we know that we can take out some part of A0 and make the set even bigger. That leftover part is called A1. And we want to make this A1 to have a measure as large as possible. I mean that is it could be bigger than this A0 by some positive number, and we said the smallest possible choice of the N1 gives us the largest number, right? That means that the A1 is chosen such that it's bigger than the A0 in the maximum way. Okay, so that's the A1. And given that, we know that A1 is a subset of A0, which is also a subset of N. We can find a subset of A1 that when we take that part out, the measure of the leftover will be even bigger than the A1. Okay? So we can choose the smallest integer N2 such that there exists a A2 that is a subset of A1 such that the measure of A2 is bigger than or equal to the measure of A1 plus 1 over N2. Okay? We can just keep doing that, and then we get a sequence of sets, and the one is nested in the previous one. Okay? Then we will obtain, we have this A0 is biggest than n1 and a2, such that the nu of ak is bigger than nu of ak minus 1 plus 1 over nk. Okay, now we know that the nu of a0 is with its positive value, and it cannot be positive infinity as we said in the beginning. We consider this to can only take negative infinity as well. It cannot take the positive infinity. That means this one is a finite number, is positive but a finite number. So you can see that this one has a positive finite value, and it is nested in this way, so we know that the limit of this sequence has a measure equal to the measure of the limit. So we let A to be the intersection of this AKs, which is the limit of this AK. Then we know that the measure of A is equal to the measure of the limit of AK. But this is equal to the limit of this measure. And this is true because the nu of A0 is a finite number. Okay? We need that to have this. You will have a decreasing sequence. Okay, and this is equal to what? Remember that we're kind of taking a telescope sum, because this is essentially just the sum, the limit of should I say this? You can think this as the limit of this nu for A0 plus the sum of j from 1 to k, nu of A j minus nu of A0, aj minus 1. Right? And this is equal to the nu of A0 is independent of k and is finite, so we can pull it out, plus the limit of the difference but here we know that this one is bigger than or equal to 1 over nj. As we showed here, for each k we know this, right? So it's bigger than or equal to 1 over nj, and this sum is just bigger than or equal to the limit of sum j from 1 to k and 1 over nj. This k goes to infinity. But this one here is just the infinite sum. I changed it to k. It's from 1 to infinity. Okay, so that means, I write it down, it's just the nu of A0 plus the sum of 1 over nk is from 1 to infinity. And now you can see that this one is finite, because we know that it's positive, but it cannot take a positive infinity as the value. And this one here is also a finite value. So both of these two terms are positive finite values. So their difference is also positive finite. So that means that the sum of 1 over nk is a positive but finite value. And this means that the nk must go to 0. Right? The nk must go to 0 as k goes to infinity. Right? If there's a subsequence that's bounded away from 0, then we know that this one, the sum here, cannot be. If there's a subsequence of this that bounded away from 0, then we know the sum of this cannot be finite. So that means every one of them must go to 0, and that means the nk must go to 0. Goes to infinity, sorry, goes to infinity, as k goes to infinity. Okay, then with this fact, we can make the following deduction. We consider the limit set E here, limit set A here. Now consider A. We know that this A has a positive measure, right? As we just showed, it has a positive measure, positive but a finite measure, but it's a subset of the n. So I know that there exists. So we know there exists, say, a subset B, which has a negative. I would say, let's consider B as a leftover. The B is a subset of A, but it has a larger measure than A itself. Okay, so there exists B, it's a subset of A, and is n such that the new B is bigger than the measure of A plus 1 over n. Okay, we know this. But on the other hand, we know that the nk goes to, so this n is for that B. So let's say there exists n of B. So it depends on the B, choice of B. But remember that the nk goes to infinity. The nk goes to infinity. So I know that for some k, the nk will be bigger than this nb. Right? So there exists, since nk goes to positive infinity, we know there exists k such that the nk will be bigger than nb. Alright? And then in this case, since A is a subset of the corresponding of the AKs, the A is a limit of those AKs. So it is inside each of those AKs. And then we have that the B is a subset of A, and it's a subset of AK, actually AK minus 1, such that the measure of B, we know that is bigger than the measure of A plus over NB, and is bigger than, because NK is bigger than NB, so that's why this is bigger than A plus 1 over NK. But remember that the measure of A is bigger than any one of them, right? Because this sequence has an increasing measure. This is less than that, and this nu of A1 is less than nu of A2, and eventually they are all less than the nu of A. So that's why this first term is bigger than, at least bigger than equal to nu of A k minus 1. Actually, it's bigger than, but it doesn't matter since we already have a strict greater than before. It's bigger than this. So what we have done so far is that we found a subset of A k minus 1, which is this B here, such that the nu of B, we can find the NB which is even smaller than the NK that we found earlier, which was supposed to be the smallest value. The NK was supposed to be the smallest value, but right now we found some NB which is even smaller, such that this subset B here has a measure bigger than this nu of A k minus 1, 1 over NK. Then that is a contradiction to the choice of the NK and the choice of AK we found before. So this is a contradiction. Which contradicts to the choice of NK and this AK. So because of this contradiction, we know that this set N cannot be nu negative, must be nu negative. Now we show that P is nu positive, and the complement of P, which is this n, is nu negative. And that completes the major part of this theorem. And the only thing left is that the uniqueness about this decomposition. So that's the third step. Suppose we have another pair of Han decomposition. Then we know that the P minus P prime, this is a subset of P, right? A subset of P. So we know that it must be it's nu positive, or yeah, it's mu positive. Okay, it's a subset of P. Well, it could be nu null, but if it's nu null, then it must be nu positive and nu negative. And if the set is nu positive and nu negative, then it must be nu null. All right. So we know that P minus P prime is nu positive, but on the other hand, we also know that we'll take on the other hand, we take the P prime minus P. And remember that this will be a subset of n. Okay. Sorry, it's a subset. Yeah, it's a subset of n. Sorry, I should say I still get this. This P minus P prime is a subset of n prime. The reason is if you consider anything, this must be something that is not in P prime, so that must be in n prime. So it's in n prime, that means the P minus P prime is also nu negative. And because it's both mu positive and nu negative, we know that P minus P prime is nu null. And similarly, we know that P prime minus P is nu null. So the union of these two is also nu null. But the union of these two is just the difference, symmetric difference of these two sets, P delta P prime is also nu null. Okay, and similarly, you can show that the symmetric difference of n and n prime is nu null. Okay, and that completes the proof. The decomposition is unique in this sense, up to this sense.